I'm starting to think that game devs are in agreement with GPU manufacturers, probably putting some invisible bloat in their games just to tank frame rates and sell newer GPU.
These are the official PC specification requirements for Monster Hunter Wilds. Yup, in order to play this game at 1080p with medium settings, we're expected to utilize frame generation.
Do you remember when the GTX 1080 Ti dropped? It was amazing for its value and its performance.
The greatest card that NVIDIA's ever made.
GTX 1070, 1060, all great cards. AMD was even making an RX 580 and 480 around this time. You'd be lucky to get any decent generation of anything on PC.
So that brings us to our question. Is native resolution always the best image quality? You can see with the examples here, that is fiction.
Can't imagine a game more complex than Cyberpunk 2077 to run, yet somehow every next new released game, regardless of developer genre series, raises the bar for requirement hardware. Someone should investigate this family-friendly show. So anyway,
PC gaming is slowly destroying itself. NVIDIA destroying game optimization to sell you new GPUs. How NVIDIA killed PC gaming optimization through DLSS and frame generation. And then you have NVIDIA's official YouTube. Is native resolution always the best image quality? These days, everyone's hating on PC gaming, supposedly something that's killing optimization, pricing in general. First, we'll talk about Vex's video. In Vex's video, he talked about the GPU stagnation, CPU stagnation, and how games are becoming more and more demanding. And something interesting he brought up is Moore's Law. And he's saying that Moore's Law is dead. Now, he doesn't necessarily claim this. He's just saying people are saying this. And he doesn't make a lot of conclusions in his video. He's just kind of bringing up these topics. And I want to talk about it today because everyone's, all these YouTubers like Daniel Owen and then Danny Z Reviews, my boy Danny Z. Shout out to him. You're welcome. I'll give you all my subs. Is upscaling techniques killing game optimization, right? Because we have these games coming out and they don't look really that much better than we used to. A game like this, you're gonna get probably 1/4 of the frame rate as you would a game like this. And honestly, let's just pause it here. Pause it when he's not moving too much. Do they look that much different? Honestly, I'm not sure. Like, it doesn't seem like that big of a difference to me, especially for getting 1/4 of the frame rate. So that is what this is all about. They're saying that game devs are relying on DLSS and even on NVIDIA's own official channel. They're saying that, hey, DLSS is better than native. There's no reason not to turn it on. Just model your games after that. And, if you can't get 60 FPS, just use upscaling and you can get there. It's kind of ridiculous what we're, at the point we're at. But honestly, guys, I'm going to agree with what this guy says because, if you take a look at this video, DLSS just does look better, and it has something to do with anti-aliasing. Anti-aliasing, there's a ton of shimmering in the distance, and with DLSS, it just removes all of that. This picture here looks so much more blurry than this one on the right. So you're using a lower base resolution, but because of AI, it actually is much more detailed and way less grainy, and way less washed out, in my opinion. So I'm gonna give it to NVIDIA on this one. I've tested this myself. DLSS quality does look better than native. That's still no reason to optimize your games around DLSS quality. And, we have here on these requirements, thanks again to Danny Z Reviews for this video. It was great. We're looking at a 6700 XT for 1080p 30 FPS, basically, guys. And that's just, it's not good. It seems like a lot of these games are actually also running into CPU bottlenecks, which that's a whole nother can of worms. In Vex's video, he talks about the stagnation of GPU and CPUs, and he's talking about, is Moore's Law dead, and are we just gonna have to get used to 5 to 10% gains for the rest of our lives here? And I'm also gonna have to disagree with this. I don't agree with this take here. Because I just did a Google search and I said, is Moore's Law dead? And basically what Google told me is it will be obsolete by 2036 based on computational capabilities. And there's some Heisenberg principle, which basically just means that once we get to these parts that are so small, like electron, we don't actually know exactly where it's at a given point in time, and that can mess up computation. So theoretically, an electron could be in multiple places at once just because it's so small, is kind of what that principle says. And I like this article here because it recognizes that there's other things that can extend Moore's law, and that being like quantum computing. Specialized architecture is a really big one, you know, coming in with ASICs and things that are like bespoke silicon that's like designed to do a specific thing and that thing only, and it can do it hundreds of times faster. You can think of a GPU, which can do many things in parallel, including AI, or an NPU, which really just does AI, but it does it much better than GPU per silicon die space, and it does it with way less power. So something like that. It also says like some crazy stuff like spintronics, which instead of using just plain electrons in a positive or negative state, uses the electron spin to compute things, and that's way over my head. But yeah, so computers are going to be eventually limited by their physical restrictions based on these principles. He basically says that after 1 nanometer, and you know, it's not necessarily him saying this, but this is what he's just giving thoughts on. After 1 nanometer, quantum tunneling would say hello, and we can't really get smaller than that. I don't know what quantum tunneling is, but I do know that we would get leaky transistor gates, and basically that just means that electrons would leak from transistor to transistor. And if you thought the 13th and 14th gen instability problems were bad, this would be like that on steroids. You wouldn't be able to do anything with leaky transistor gates. Now, it's important to note that like TSMC 4 and 5 nanometer is not actually physically 4 and 5 nanometers, so we can get smaller than their like 1 nanometer node, for example. But we are getting really close to the physical limits and the size of gates. Now, the real question is, are we going to be limited by transistor density, right? If we can't get any more transistors in a given die space, will we just see no more performance gains? And guys, in my opinion, this is just totally nonsense. Like, shrinking transistor size is only one way to get more performance, and there is like a handful of different ways where we can honestly, guys, get hundreds or even thousands more times more performance than we have now. 20 years ago, we didn't even have smartphones, and now we have phones that are stronger than supercomputers that took up like a football field. Well, I think another 20, 30 years from now, we'll be looking at the same thing where our mobile devices will actually be as strong as supercomputers now. And there's a couple of reasons why I think that. We can talk about it. First lever we can pull to actually get much more performance out of our semiconductors is changing the substrate. Right now we're using silicon for a semiconductor, and silicon's really great because it has an optimal band gap. Well, I shouldn't say optimal, but it has a great band gap for transisting to on and off state, and that's why we can program those gates to do whatever we want. But graphene actually has an even smaller band gap than silicon. And if you don't know what a band gap is, we can go over it right quick in this video. But basically, insulators have a large band gap, and that means it takes a lot of electricity. Let me go back to that. It takes a lot of electricity for an insulator to conduct. Basically, the electrons like to stay close to the atom on an insulator. A semiconductor, that band gap, aka the resistance of the material, is much lower, but on a semiconductor, the band gap's wide enough to where you can kind of control whether it's an insulator or a conductor. Okay, so that's what makes semiconductors really great for computing. And in a conductor, there's no band gap, aka it just completely lets electrons pass through it without any resistance. Now, what makes graphene so special as a new medium for semiconductors is its band gap is so small that for the amount of electricity it takes to flip a transistor is actually 1/10 of silicon. So basically, think about a chip that uses 1/10 of the power but is just as fast. Yeah, that's graphene, but this can actually be a problem because it takes so little electricity that, well, it's kind of hard to program, and it actually can be leaky. So you'll turn on one switch and it conducts electricity so well, it can actually turn on multiple switches, and it causes all kinds of problems. Or they bind graphene to a silicon wafer through these little nano ribbons, and that actually makes it have an appropriate band gap where we can control conductance, and it makes it really good. So guys, think about graphene as a new medium that we can get 10 times the performance and 1/10 of the power consumption just by changing mediums to graphene. They are saying that this chips with graphene based medium can get in the terahertz range. And if you don't know how much that is, 1 terahertz is 1,000 gigahertz. Okay, so if you think your chip with 5 or 6 gigahertz is quick, think about a chip getting 1,000 or 2,000 gigahertz, guys. Yeah. Now, I'm not sure. It's really important to say, like, you know, our memory technology and our connection and our I/O would definitely not even be able to have that much instructions in a given time period. So we definitely have to rethink how we build and how we shape computers if we went over to graphene. But yeah, so the main reason we haven't gone over to graphene, if you're wondering, you know, this has been around for, I think, a decade. We've known about graphene, is the band gap. But like I said, recently they found a way to increase the band gap just a little bit to where it can actually be useful. And let me just say, that's the best thing about using graphene as a medium is it's compatible with the fabs we have now. Like, yeah, that's right. If we have a fab that can produce 1 nanometer or 2 nanometer silicon wafers, well, it's actually just a plug and play for graphene. A fab that works with 2 nanometer silicon wafers will also work for producing graphene in 2 nanometer gate size as well. Guys, that's huge. And this, I think, we'll be using in the next, probably in the next 15 years. I think we will switch over to graphene, because as we get closer and closer to that gate size limit, the physical limit, we're going to need a new medium. And graphene's looking very, very promising, guys. And overall, I think at scale, it's going to be much cheaper to produce than silicon once it actually gets up and going. As far as like Moore's Law, you know, if Moore's Law is dead, based on its definition, it very well may be dead, because a 5.2 gigahertz processor was built in 2010 by IBM, and basically if we followed Moore's Law, by 2050 we'd have a processor that's 5.5 petahertz, and that's not terahertz, that's peta. So 1 petahertz is like 100,000 gigahertz. Yeah, so that's like 500,000 gigahertz, and I don't think we're going to reach that by 2050, guys. I think we're going to pull other levers just in clock speed, but that's just something to say. So I don't, especially for like the price of Moore's Law, because Moore's Law also says that we'll get double performance at the same price. That's basically getting the same performance at half the price every 2 years. And I don't think necessarily we're going to hit that. I think the economics at scale for this kind of stuff has gone out the window with how expensive fabs are to produce. And well, let's just be real, how greedy these companies are and capitalism, how it works. The money side of Moore's Law, I think, is dead, and I don't see that really coming back into play. But as far as the performance side, I think, yeah, we will see on average a doubling of performance every 2 years. If you look 20 years from now, I think we will see that, guys. I don't think it's going to slow down, especially with how greedy these companies are getting. If you really want to upgrade, yeah, quantum computing can be hundreds or even thousands of times faster than classical computing at certain tasks. And those tasks use like probability based. It's not a 1 and 0. It's based on a qubit, which can be 1 and 0 at the same time or anything in between that. And yeah, quantum computing, I think it's going to have its place. It's probably going to be its like own piece of silicon on like a die, separate from classical computing. And yeah, I think that it's going to be basically like accelerator for certain programs that use it. I think AI will in the future use quantum computing, because based on what I read about quantum computing, based on its probability-based calculations, it sounds like it would be really good for AI. So that's another lever we can pull to get literally thousands of times more performance than we have now in certain applications, guys. So if you look at graphene getting 10x performance, quantum computing getting 1,000 more performance, we haven't even talked about photonic computing. Instead of using electrons, we can use a light, and that will give us hundreds of times more performance than we have now. So guys, we are not limited just by the gate size. We can get a lot faster and a lot more performance than we're getting now. honestly, we just have to get creative with how we design semiconductors, because so far these last 20, 25 years, sure, I think in the past 10 years, we've had a lot of design changes that give us more performance. But other than that, we've just been relying on that gate size, and it's not going to cut it anymore, guys. The last thing I want to talk about is memory and IO access, because I think that's the biggest thing holding back computers right now. And it's going to be, I think, the lowest hanging fruit for us to pull in the near term to advanced computing. Let me tell you what I'm talking about when I say IO access. IO access and memory bandwidth are the number one thing holding back computing right now that I think is like the easiest thing to fix. So I think that IO access and memory bandwidth and just how we do computing right now, this is the first thing that's going to change before we change mediums, before we go to quantum computing, before we use photonics, any of that stuff. We're going to change this first. So this is the nearest term solution to advance Moore's law. So I just have this little drawing here I've done in Microsoft Paint, and I have a Ryzen CPU, a modern Ryzen CPU, and a modern Intel CPU. So first we'll talk about the Ryzen CPU. We have these two chiplets, and those have 8 cores each, okay? So 16 core CPU, and then we have an IO die here, okay? So anytime that we need to access data and actually use the CPU cores, we're going to have to go from the IO die to the CPU cores. And to even get information to this IO die, we're gonna have to go to the RAM, then go back to the IO die, then go to the GPU, and then come back to the IO die once again. Okay, so that's how all this is gonna work. And if you need to communicate these two cores, you're gonna have to go through these wires here. And these wires are very primitive. They're similar to the wires you have for PCIe connectivity. And then you'll go through the IO die and then come back to this chip. And that's how you would communicate. That's why there is so much latency on the newest Ryzen CPUs, because this Infinity Fabric technology is something really just out of like 2012 technology, and we shouldn't be using it anymore for transistors we have this quick. So if AMD comes out with a new CPU design, something other than Ryzen, expect them to fix this first, because it's really primitive and it slows down their CPUs a lot. Okay. And then we have a modern Intel CPU. This is monolithic, right? It's just one piece of silicon, and this makes latency a lot lower for this chip. And it actually, so if any part of this chip needs to communicate with any other part of this chip, it just travels through silicon. It's much, much quicker than these wires and traveling all this physical space. But there's still limitations to that, guys. I have a modern motherboard here, and it could be either, an AMD or Intel CPU. That's why it's red and blue. And in this, we're going to have to access this RAM here, which is actually physically pretty far from the CPU. And that's how we're going to access our memory. And not only that, this is not a huge, like the memory bandwidth of this is not actually too large. It's, if you're on DDR5, it may be a little over 100 gigabytes a second, maybe 120. If you're on DDR4, it may be, 60 gigabytes a second, or even as low as like 40. Okay, so you need that. You got to go there. And then you got to go all the way down to your GPU, which is also a lot of physical space, and that adds latency, and it limits your memory bandwidth compared to using something like just silicon interconnects. And honestly, guys, this is so inefficient. Okay, let me move myself. This is so inefficient. It could be so much more efficient than what we have here. There's a lot of levers we could pull before we even touch die size. You could have something on the same node and make this literally like 30-40% faster, guys. Okay, so now we're going to talk about a modern CPU architecture. This is Lunar Lake, and I hope, let me move myself here. Or maybe I should move myself. Okay, so this is Lunar Lake. It's a modern CPU architecture, and this is getting, it's getting to the point with what I'm saying here. We have to get smarter on how we design semiconductors, and that's exactly what Lunar Lake is doing here. And it uses the interconnect. It's using chiplets, right, which adds latency, But instead of just using these primitive wires and like a large distance from the silicon, it's based on a silicon interposer. That's what this purple part is here. So all these little chiplets are sitting on a big piece of silicon and they communicate through that silicon, right? So you have like CPU cores, GPU cores, IO, and like a dummy die, and you have all that on here. This isn't like an accurate sections of Lunar Lake or anything. I just drew it up right quick. And then you also have your RAM, very high bandwidth RAM, right by the silicon here. And that makes it super low latency and really, really high bandwidth, high signal integrity. And you're doing all this on a super small chip, right? Like, it's not like this is a lot of silicon, but it performs really well for how little silicon you use. And also it uses less power, less latency, more performance. So you can probably see why that's a much better setup than we have here. Now, that's going to be more limiting because everything's together. You have, you're spreading everything out here, so you can generate more heat. But we can talk about what I think the future of, oh wait, let me go to the side here. What I think the future of computing on desktop may look like, guys, because I want to talk about this. We could stay on 2 nanometer for like 5 years and we can get much more performance if we follow this method, okay? So this can give us a lot more performance. Let's talk about it. We have a motherboard here, and then unfortunately we are going to have to solder these components on the board, but we're going to have a big silicon interposer, okay? This large silicon interposer, and then we have a CPU tile right here. Then we have a GPU tile, and this GPU tile is much bigger because I think more and more things are become accelerated by the GPU. And then we also have an NPU or some sort of accelerator. This could be maybe IO, media encoders, any of those different things could be on this tile right here. It's just another piece of bespoke silicon that is designed to do one thing, and it can do it really well. And then we have our memory modules here, and those are connected on the silicon interposer through very high bandwidth. You could even do like a 2000 bit bus right here and just get crazy performance. So everything you need for your computing experience is on the silicon interposer, super high bandwidth, super low latency. And guys, I think that level of computing, even if we stay on the same node, you can get 50, even 100% more performance if you do it this way. That might sound crazy, but just think about how much more memory bandwidth you can get and how better lower latency activity you can get. So with certain applications, I think you could get that much more performance. And that's not even introducing any of the things we talked about, like a medium change to graphene or quantum computing or photonics or anything like that. Now, this would just all be soldered on this board, but you could still buy a motherboard like this, slip it in your PC, and then there would be PCIe slots for something like USB cards or Ethernet cards, capture cards, those kind of things that the latency and bandwidth doesn't really matter as much. And guys, this is where I see computing going. I know you might not like it, but for me, I think sacrificing these kind of things to get the level of performance we want is just going to be a necessary evil, guys. I really do think in the next 10 years, we will be seeing things like this. And I'm okay with it, really, if it's using half the power and giving us double the performance, really. And theoretically, I know you're thinking, well, this is not going to be a lot of silicon if you do it this way. You can make this die as big as you want. You're using chiplets here. This could be a 400 millimeter squared GPU, 100 millimeter squared CPU, and then whatever size your bespoke silicon. And you could add GDDR memory on here, get tons of bandwidth, do whatever. It's all customizable. And I think that's the future of computing, guys. It's much better than this strategy we have now. This strategy is outdated. It is very modular, but you're sacrificing so much performance. And, if we're really getting to that gate limit size, we're going to have to make a change. Okay? So the question, is Moore's Law dead? Is PC gaming slowly destroying itself? Well, and then DLSS optimization, all that. So we can start with Moore's Law is dead. Guys, I think 10, 20 years from now, we're going to be looking at PCs hundreds of times faster than ours. Ours is just going to be blown out of the water. We talked about all the things that can contribute to this performance. And if you don't think these trillion-dollar companies are going to invest in actually pursue these things, you're just wrong. They're going to give us the level of performance. Now the pricing thing is tricky. I think performance will skyrocket, but then price is going to skyrocket with it. So, Moore's law does consider price, and if you look at it from that standpoint, it probably will die. But as far as performance goes, no, I think it's going to just be exponential as always. The stuff we have now is going to be really slow compared to what we're going to have in 20 years from now, especially if they use all these levers in the short term, like I was saying. And then, just a medium change to graphene alone, which will be compatible with our fabs that we have now. It's just going to give us 10x performance and so much lower power, which we didn't even talk about, but for mobile is a godsend. It will be amazing for mobile. Okay, so that answers that question. Vex, I'll see you later. You're welcome for the shout out. And then Daniel Owen, is NVIDIA destroying game optimization, sell you GPUs? I think this is just a matter of some lazy developers, because I gotta admit, dude, games don't look that much better than they did 5 years ago, but they're literally twice or 3 times as hard to run, and it's kind of unacceptable. I think all we need is better game scaling. That's all we need. Like, at the very lowest settings at 1080p, you should be able to run the game on a potato, no matter the game, right? And when I buy a potato, I mean like a CPU in the last like 4 years or something. I don't support like, the Xbox 360 and PS4 and all that. That's definitely holding some things back. But I just mean like, a CPU that's came out in the last like 4 or 5 years should be able to run games at 60 FPS if you turn all the settings down, guys. It shouldn't be that hard. And then if you want at the very highest end, sure, bring the 4090, 5090 down to its knees. But we need better game scaling, and that's what we don't have right now. And devs really need to work on that. They really need to leverage art style of their games and really lean into their art style more, instead of just trying to push as much pixels in something that just doesn't look good, right? So yeah. And then so this is same thing. Danny Z, he brought up the same game, and that's really my thoughts. Like, game devs do need to do better. These guys are providing some valid points here. And NVIDIA coming out with their rage bait cope. And honestly, I do think this is fiction. I don't think native resolution always does look better. I've tested it myself, guys. DLSS, especially quality DLSS, does look better than native resolution a lot of the time. There's not as much flickering. Anti-aliasing looks a lot better. This is true, dude. Like, native resolution is not always the best looking. And if you don't have an NVIDIA card, you may just be crying in your seat right now, but it's true, guys. Like, get one and find out for yourself. It's true. Let me go back to paint here. Overall, I think we're gonna have to change the way we think about computers. These old forms of silicon design are just gonna have to go out the window, guys. Like, we need to do better. We need to do better with game optimization, supporting a wide stack, and we need to do better with how we design silicon and we design semiconductors. But that's just my thoughts. I think 20 years from now, your PC is going to be garbage and you're going to need something like 100 times faster. But hey, maybe I'm wrong. Let me know, guys. Are we just going to see stagnation, 5-10% gains for the rest of our lives? Or are we going to see huge increases still 20 years from now, jumping to graphene, jumping to photonics, jumping to quantum computing? And like, something I was going to say is like, in something like this, like on a motherboard, like this chip could be a quantum computer. Like, I don't know if that would be compatible. I'm just saying, like, you could add a piece of silicon that does quantum calculations, or, a piece of silicon that uses photonics instead of electrons. And that will probably be really good for certain applications. It's just something to think about, guys. And even if it doesn't support it on here, you could pop it in the PCIe link. And I think, creating different pieces of silicon, different pieces of semiconductors for whatever task you need, we can get hundreds of more performance, guys, like 100 times more performance. It's not going to stagnate anytime soon. I really don't think it is. And if it does, I guess I'll just hold on to what I have and my old basic setup like this, Are we going to be looking at this forever? Are we going to jump to something like this that's a little bit new, a little breaks the mold? And is DLSS worse than native res always? Are people killing game optimization? And is Moore's Law dead? Let me know down in the comments below, guys. Silicon Steak, signing out.
Once upon a time in the land of silicon dreams, we pushed the boundaries, or so it seems. But now the law of more has met its end, and death they just pretend to land.